origins. We'd like to understand how life arose on Earth.
And now science believes it has the answers. It's even built the biggest machine on Earth to recreate the beginning of time. Take a virtual shuttle ride back to the Big Bang. Our universe is an elegant ensemble of over 1 billion galaxies, each cradling some 100 billion stars. It's still uncertain how many planets exist. We know Earth takes up residence in the Milky Way galaxy. Our blue planet orbits our sun like a sapphire jewel, the only celestial body known thus far to harbor life. But how did our world get here in the first place?
Ultimately, we want to understand what it was that produced the universe and how it evolved over the 14 billion years of its existence.
For the first time in history, scientists have answers to some of these questions, in the sense that the universe is everything that we know about, everything that we see. And what the Big Bang does is tell us, how did we get here?
The Big Bang Theory says that over 13.7 billion years ago, our universe began at an incredibly dense, hot, compressed state with one main mission: expansion.
There was a cosmic explosion that created the stars, the heavens, the galaxies around us. So everywhere we look, we see remnants of this cosmic explosion which set into motion the universe.
The Big Bang is now a well-accepted physical theory to explain what happened after our universe was born. It's substantiated with sound scientific data and observations.
A theory isn't just any old idea that you dream up in the middle of the night. Only after it has satisfied many tests does it get elevated to the status of a theory.
If you look at the Big Bang Theory, we just don't have one data point. We have hundreds of data points that fit exactly the Big Bang Theory.
When we look up into the night sky, we can rewind time all the way back to the Big Bang itself. When you first look up in the sky, you see stars, and you might even see our own Milky Way galaxy. But if you look still farther away, you see the cluster of galaxies. Looking back even further still, you can see the very first generation of stars being formed and dying. If we keep going back in time, we can see the very first atoms forming. Continuing our journey back in time, we can see the formation of the first protons and neutrons. If we keep rewinding the clock much further past that, we can look back to the very first instant of the Big Bang.
How was the discovery of the Big Bang achieved? Why do we know it to be true? And what do we have left to learn? For hundreds of years, astronomers have stared into the starry night and contemplated the origin of the universe. But most ideas contained religious undertones. By the 20th century, science finally began to assemble the pieces of this age-old puzzle. In 1915, Albert Einstein, perhaps the most influential scientist of our time, was fascinated with our universe. To him, there wasn't a beginning or ending. Einstein believed the universe was infinite and eternal. Yet Einstein's personal beliefs contradicted his equations that indicated the universe had a beginning. Einstein's theory of general relativity predicts that gravity is woven into the fabric of space and time, or space-time. When introducing mass into a stationary universe, gravity will eventually pull all the matter in the universe together. In other words, galaxies would fall on top of each other. On the other hand, the universe can be expanding if it was born in a state of expansion.
Einstein thought that the universe is static, and such a hypothesis was aesthetically pleasing to him. So he actually introduced a mathematical fudge factor into his equations that didn't make them wrong, but gave a very special solution, a very unlikely solution, a static universe.
Einstein called this fudge factor the cosmological constant. The physicist proposed that there's a repulsive effect to counter gravity to maintain a static universe. This cosmic variable satisfied the scientific community, who at the time had a narrower view of our world.
If you were to ask an astronomer back then, what is this universe of ours? They would say, that's easy. It's just the Milky Way galaxy. That's all there is. It's not moving. It's simply uniform and static.
Einstein's ideal model of a static universe was soon shattered. In the 1920s, at Mount Wilson Observatory in California, astronomer Edwin Hubble peered through the biggest reflecting telescope of its time. It enabled him to look farther into space than ever before. Hubble was amazed to discover that there were thousands of galaxies beyond our Milky Way. He did this by measuring the brightness of distant stars compared to stars close by when observing their red-shifted electromagnetic radiation.
Everybody's familiar with the sound that a car makes when it drives by you, as it passes. That's the wavelength of sound being stretched as the car is receding or approaching you. Light waves also do the same thing. When an object is moving toward us, it becomes bluer. And when an object is moving away from us, it appears reddened. This is called redshift. So by observing how red something appears to be, astronomers can get an idea of its distance.
So here's a hypothetical universe expanding after the Big Bang. It's kind of like our universe, where the stickers are the galaxies and the rubber is the space in which the galaxies are embedded. This is exactly what we see in our universe, where the galaxies are moving away from one another.
Hubble proved what Einstein's calculations had long predicted, but what the scientific genius was reluctant to acknowledge.
But then when Edwin Hubble finally showed that the universe was in fact expanding, Einstein said, this was my greatest blunder.
Hubble's discovery of an expanding universe, known as Hubble's law, became the first piece of evidence that would support the Big Bang, a theory that came from an unlikely source. Georges Lemaitre, a Belgian priest and physics professor, had studied Einstein's equations. He calculated if the universe is expanding today, it must have been smaller in the past. Therefore, it must have had a beginning. Lemaitre proposed that our expanding universe emerged from a primeval atom.
He understood the implications of Einstein's idea that if the universe is expanding, then perhaps it had an origin in some kind of cosmic primordial atom or some kind of cosmic egg that hatched, giving birth to the universe.
Georges Lemaitre's colleagues did not think much of the primeval atom. It suggested a creation event which perhaps borders more on religion and theology. They preferred that the universe either be static, as most people had thought before that, or perhaps eternally expanding, if it really is expanding, as Hubble showed.
Lemaitre defended his primeval egg theory as purely scientific. But British astronomer Fred Hoyle staunchly opposed his hypothesis. While he agreed the universe is expanding, Hoyle proposed that new galaxies are formed from matter that is constantly being made. So the universe has always existed and always looked the same. Hoyle called his alternative theory the steady-state model.
Fred Hoyle, in fact, accepted the observed fact that the universe appears to be expanding. But he said there was no creation event, there was no beginning. The universe has always been expanding, and it will forever continue to expand.
In 1949, during a London radio show, Hoyle tried to contrast his steady-state model with Lemaitr's idea of a primeval egg. He referred to Lemaitr's theory of the Big Bang idea, and the name stuck. These two competing theories would become engaged in the ultimate scientific duel to determine the origin of everything. By the middle of the 20th century, the origin of our universe was still a big question mark. Two opposing theories were at the heated core of this scientific battle. Fred Hoyle's steady-state model and Georges Lemaitr's Big Bang idea. In order for either of these theories to be proven, each must explain the origin of elements in the universe, the stuff that everything is made up of. There are light elements, primarily hydrogen and helium, and heavy elements, such as nitrogen, carbon, oxygen, and iron. Under high temperatures, the light element of hydrogen fuses to form helium. In turn, helium fuses into the heavier elements. Fred Hoyle proposed that the creation of all these elements, heavier than hydrogen, happened in the cores of fiery stars in a process called nuclear fusion. This also included the second most abundant element, helium.
Willie Fowler, who's a nuclear physicist, and Fred Hoyle, and they explained how stars make the elements. And so then they thought, well, stars also make helium, so you could just make all the elements in stars, and you didn't need to have a Big Bang.
But Hoyle's theory had several glaring problems. Most importantly, it didn't explain how hydrogen was formed, because the earliest stars must have been formed with hydrogen already present. Hoyle dismissed this problem by suggesting that hydrogen and helium had always existed and were always spontaneously being created. But others began questioning Hoyle's hypothesis. In the 1940s, Russian physicist George Gamow also studied the origins of chemical elements. Using the Big Bang theory, he predicted the relative proportions of hydrogen and helium in the universe, and found that it should contain a lot of helium, which only can be created by fusing together two hydrogen atoms. Gamow discovered that hydrogen makes up nearly 75% of the elements in our universe, and helium only 25%. He concluded that stars alone couldn't generate so much helium. But if the universe began with a hot, dense Big Bang, temperatures would have been high enough everywhere to fuse hydrogen into helium.
If you look at what's called primordial clouds of gas, they have what is probably the original proportion of hydrogen and helium. And that's roughly 3/4 to 1/4 hydrogen to helium. And that's what the Big Bang theory predicts.
The origin of heavy elements from the fusion of lighter elements became known as nucleosynthesis. It's the second line of evidence supporting the Big Bang theory. But George Gamow went one step further.
Physicist George Gamow and his students made a fantastic, startling hypothesis. If the universe was very hot at the instant of the Big Bang, then today there should be an ember, an afterglow.